Hello, guys. Um, so sorry it's been a little while since I posted a video for numerical methods, or sorry, for programming, but I'm busy with getting stuff up for my other courses. Um, so just to give you a heads up, I've been kind of with all the changes. It's kind of forced me to change some of the topics we've we're going to cover, and um, we're probably not going to hit all the topics I would have hit otherwise, but I think mostly the things that we won't quite get to are in applications of programming, little projects and little things you can use programming to do. We've already hit the key concepts that we needed to learn as far as how to program and how to get the computer to compute numbers. So coming up, we have this video, which is on something called the bisection method, which is a method of solving equations, in particular nonlinear equations that would be really tricky to solve otherwise. Then next up, we will talk about how to get a computer to at least approximately take derivatives of functions, and we'll talk about that. And that's going to be a really important video because it will explain key concepts that you're going to need for the last two. So make sure you pay attention to the video on numerical differentiation. And then the last, I don't know, I suppose we'll call it a lecture period, we'll be discussing how you can use some of these ideas to write programs to solve differential equations. And the key examples I will want to talk about are differential equations that come from physics, specifically Newton's second law. And so those will be the last of the lecture topics for the semester. And then we will have one final large project. So each of these lecture videos or lecture files, if you want, which you can get off of Blackboard, will have problems at the end. So for example, this one here is going to have some homework problems. I suppose just one, sorry. So there'll be a homework problem for you to do. And then you'll be expected to submit those via Blackboard. And then there will be one final project, and I kind of went back and forth on what the final project should be, and ultimately I settled on having you guys try to simulate pandemics and the spread of viruses. So anyway, so I thought you should know that's kind of, so that's what we have left standing or outstanding for the semester. So hang tight and push through. You're almost done. If there are any questions, I will still be around during office hours to answer questions about either these videos or the files or the homeworks or the project. But that's kind of a list of what all we will be doing for the rest of the semester. And as we discussed in this course, there is no final exam. So just finish the last project and that's how it will go. Okay, so the bisection method is what we're talking about in this video. So the bisection method is a way to solve for when a function equals 0. So the first thing you have to do is you need to write a function for some function of x equals 0, and it produces x. Okay, so it's kind of like if we had a parabola, we would just use the quadratic equation. But we can use this method for other really complicated functions, transcendental functions, functions with just all sorts of gross behaviors. And this method will work. Now, sometimes you can have a function with many solutions. Sines and cosines go through zero many times. And this method will find one solution. It may not find the solution you want, but it will always find one. And if you can kind of combine this method with a good graph, usually it will work. There are other ways to do this. Each of them have their own advantages and disadvantages. There's something called the Newton-Raphson Method. I don't know. There are lots of other methods, but the purpose of this course isn't really to teach numerical methods. I just want to show you how to use programming to achieve numerical tasks. Okay, so right here I have a function, and I believe, if I remember right, that this function was x squared minus 1. So I think, and the solution is clearly at x equals 1. But let's imagine we didn't know that, or maybe it wasn't a simple obvious place where the function went through 0. So what I've done here is I've kind of cheated here, and I have made a little animation which sort of just highlights how you actually use the bisection method. But when I say I cheated, it's because to actually make this animation, I used the bisection method that I'm going to be telling you. So this is a cartoon image of what's happening. Let me make this a little larger if I can, or if I can stretch these out. Yes, I can. Oh, very good. Okay, so what we're going to do is cycle through these. So here's this curve, and we know the solution is at x equals 1. But the way this method works is as follows. You basically make two guesses. You make a guess for two guesses for possible roots, you might call it, or solutions, or the value of x where the curve is 0, the function is 0. So you might choose, so you need to choose two values. One of them has to be where the function is positive, and the other has to be where the function is negative. And this is where having a graph helps. If you chose both points to be where the function is positive, then if we're writing this in a program, you'd want to give an error message and tell the user to make a different guess. Okay, so the way this will work is as follows. We have a curve. We're going to make a guess for 2 points, one where the function is positive, one where the function is negative. There you go, like magic. Okay, so I think I guessed 1.7 here, I think is, if I remember right. And this is 0.5, and I put in little dots, and I didn't bother to unskew them, so they look a little squished, but that's okay. Now, the idea of the bisection method is that if you keep chopping the interval in half and throwing out the part that's irrelevant, you eventually squeeze down and you center the interval on the root of the equation. So the idea is going to be, we've got these 2 points. Over here, the function is negative. Over here, the function is positive. We're going to chop it, find the place in the middle, and evaluate the function at that point, at that midpoint, or where it has been bisected, you might say. If the function is going to be positive, or is positive at that place, which it will be here, then that means that the lower half must contain the interval, the solution, the root, and we can forget about the original upper point and move it down to the midpoint, the bisection value. And then we proceed again, and we bisect again. So let's go through an iteration here. So then I bisect it. Okay, that's the bisection point. And we notice that the blue at this point, at the midpoint, the blue curve is positive. So we're going to move this black dot all the way down to here. Okay, so I put in green the old one. All right, so now I have a new interval. But notice I have kept the good point, the place we're trying to find, in this somewhere in between the two black dots. Okay, we're going to do the same thing again. This time we're going to find the new midpoint, which will be about here. And you'll notice then that the blue curve would be negative. So that means I want to move the lower point up. Okay, so the lower point was over here at 0.5 and has now been moved up. And you see how the interval, which started out being at 1.7 and 0.5, has zeroed in and is squeezing in towards my solution. And if you keep iterating this over and over and over and over and over, you can get as close to this as you want. I think I may have hit all the points that I in my simulation. Yeah, that's the end of my simulation. So we can go back and kind of play it continuously, a little bit slower here. And then you would keep going, and it goes again over and over and over. Okay, so that's the basic idea. Pictorially, it's pretty simple. It's relying upon the fact that if you have a function which is negative in one spot and positive in another spot, it has to go through zero somewhere in between. That's the key idea. All right, so we're going to go through this. We're going to make a couple attempts. The first way is going to be, excuse me, I'm going to kind of go through step by step by step, not a very automated fashion. And then we will sort of introduce if-then statements, and then I will want you guys to do the last little bit to put it into use a while loop. So to do this, I'm going to define a function. It's called midpoint, M-I-D-P-T, midpoint, x1, x2. And all it does is find the average of the two, just the place in the middle. Okay, so it's just, it's going to find the middle of these 2 points. And I've just picked a function here. I picked something nice and simple. It's x cubed minus 1, because the answer is clearly x equals 1 is the solution to this, for which the function is 0. So it's nice to have that because we know the answer. Okay, and the upper point, I'm going to choose to be 1.7. The lower point will be 0.5. Okay, just as before. And then what happens, so here's my function. And then I have an upper point and a lower point, just guesses. Those don't come from anywhere special. You just, other than just maybe looking at the graph, kind of get a feel for what's a reasonable guess. And then what I've done is I defined the output of the midpoint function to just be a variable called midpoint. And you input the lower and upper point, and it spits out the midpoint. And then I evaluated the function on the midpoint. So I apologize, I think I forgot to, there we go. And it comes out to be 0.331, it's positive. So I think this is a different function, but the idea would be I go over here at the midpoint and the function is positive. So I should move the upper limit down. Okay, so what I did is, after I found that because this was positive, you might say if this was positive, then I should take the value of midpoint and put it into the associated with the variable upper point. So basically I've lowered the upper point down to what was the midpoint. Okay, and then I have just a little sort of make it a little bit easier. I've kind of printed out the lower point and the upper point at that point. And then we're going to go through it again and again and again. Okay, so I'll go through. And what you can see is, so I went through, the lower point was 0.5, the upper point was 1.1, which was the midpoint we found before. And then I evaluated the midpoint again, and I evaluated the function on the midpoint, and this time it came out to be negative. So that tells me that I need to move the lower point up to the midpoint. Okay, so lower point is now equal to the midpoint. And then we're going to print out the new lower point, new upper point, and then evaluate the midpoint. Just put that into, store it away, and evaluate the function on that same place. And I get negative 0.1426, whatever. Okay, so it's negative, so that means I should move the lower point up to the midpoint again. So I say midpoint equals lower point, and I do it again. This time, notice that when I evaluate the function on the new midpoint, I get a positive number. So that means I need to move the upper point down to the midpoint. And then iterate again. And you'll see what's happening here. Remember, the solution, because my function is x cubed minus 1, so I know the solution is 1. Look what happens to the gap between the lower point and the upper point. They sandwich the midpoint. So now I'm at 0.95, 1.025. And we can keep going. And it'll get closer and closer and closer. And you'll see that when you evaluate the function on the midpoint, it gets smaller and smaller and smaller. And after a number of iterations, I'm at somewhere between 0.996875 and 1.00625. It's getting really close to 1. And the more you iterate it, the closer you're going to be. Assuming the function is smooth, basically, you can pretty much use the value of f of the midpoint to kind of estimate your error bars. We know that all the changes are occurring in the third decimal point. So the answer is going to be good to, the first 2 digits are going to be solid, and the third decimal point after, or third digit after the decimal point is where the changes are occurring. Okay, so that's the basic idea. So what we're really just seeing, I'm kind of mechanically or manually adjusting this bit by bit by bit. So just mark 2 points, find the midpoint, evaluate the function at the midpoint, and then in this case, if it's positive, move the upper point down. If it's negative, move the lower point up. And then you've got a new interval, find the midpoint. Now in this one, it evaluates to a negative. The function is negative at the midpoint, so move the lower point up. And then keep going and going and going, and it gets better and better and better. Okay, so you might notice, so I wrote it all out here. And okay, I mean, I guess I have the magic of copy and paste, but it's still pretty painful because it's a lot of just tweaking, and every time I have to look at it and say, should I move the lower point or the upper point? And it's kind of gross. So one thing we can do is use if statements to do this, just make things a little bit easier for us. So same thing, same function. I'm going to make the same initial guess just so we can compare easily. And, oh, went a little too far. Okay, midpoint's defined the same way. And this time I'm going to say if the function evaluated at midpoint is greater than or equal to 0, well then I'll move the upper point down. On the other hand, So this is if this is true, then do this. Else, meaning if the function was negative at the midpoint, then you should move the lower point up. Okay, so I'm just have an if-then statement going through what I was saying out loud. And we just go through and iterate and iterate and iterate. And again, you can tell I haven't used a loop, so therefore I just have to have separate blocks for each one, but it's zeroing in on the same solution. If I just had the patience to keep going, in fact, I could probably just keep it shift enter, shift enter, shift enter, and we can watch. Let's watch these. Let's see what happens. Let's watch these numbers. I'm going to hit shift enter over and over and over, and we'll see what happens. All right. Closer and closer to 1. See how both points just kind of zero in on 1. Very good. So we could say, oh, that's okay. There we could see at this point, what is upper point? So really Mathematica is saying that it's 1. There's just no point. It's just 1. And then the lower point is 0.99999. Okay. And if you wanted to, you could tell it to keep more digits and you could get closer and closer and closer. Okay? So that's the idea. You keep iterating this process over and over and over. And okay, so in this little section, I copy pasted it, but wouldn't it be nice if I didn't even have to hit shift enter, shift enter, shift enter over and over and over? Wouldn't it be really nice if, I don't know, if we had a structure that allowed us to repeatedly apply a rule, like, you know, a while statement. You could do a do loop or a for loop, but really this is a place where a while loop makes a lot of sense. So the idea would be this. Imagine you had some tolerance for error. So let's say you're willing to accept an error of like 10 to the negative 5. And what you could do is specify a function, right? So what I want you to do is write a function called bisection root. You will specify the function, and then you will specify a lower guess and an upper guess and a tolerance. It would be like 10 to the minus 5. And when you do this, it will go through what we had up here where I had to hit shift enter, shift enter, shift enter, shift enter over and over and over, except rather than doing it mechanically, you're going to have a while loop, and it's just going to keep going through the bisection method until the difference between your upper and lower guess is less than your tolerance. So once the two guesses get close enough together, you just decide that that is enough. And then you want to return the, really then what you want to return is the function evaluated, or sorry, the midpoint of the upper and lower guess. Right? So you run this loop until you know that the upper and lower bounds are smaller or tighter than tolerance, and you basically just take the midpoint of the two, and that'll be the answer. Okay, so that's what I want you to do, and then the homework problem is to, I guess, first write the program here. It should be pretty easy. It's really just putting this into a loop, more or less, and then I want you to use that to solve this equation, to figure out what value of x satisfies sine of x equals log of x. And just a comment, in Mathematica, when you type log of x, that is actually log base e a natural log. If you want base 10, you have to hit comma, you have to type comma 10 to get base 10 log. But I don't want that. I just want natural log. Okay, so when is sine of x equal to log of x? And that's a problem that you can't solve by hand because those are both transcendental functions. But the little program you write here, bisection root, it won't care at all. It'll just crank out the answer as accurate as you want. All right, so that's all for this video. I will be sending an email with deadlines for things, but hopefully that makes sense to you, and hopefully it gives you a better picture for what's going to happen over the rest of the semester. All right, see you guys next time.